most of the time, when I talk about probability, people think pick a card, roll dice, play a game. Those types of probabilities refer to discrete probability. So a discrete idea is one with a finite number of outcomes. Now, mind you, that finite number could be mind-bogglingly huge while still being a finite number. If I tell you flip a coin, how many outcomes are there?
2 outcomes.
If I tell you to pick a card, there are 52 outcomes. If I tell you to shuffle a deck and take 5 cards, there are 2.6 million outcomes. If I tell you to shuffle the deck and take 13 cards, we're playing hearts or spades or something like that, we got a lot more options. By the way, if I tell you to shuffle the deck and rearrange those 52 cards, there is a not insignificant chance that you will create an ordered arrangement no one else in the universe has ever done. Because if you count all the different ways to shuffle a deck, that's 52 possible first cards, 51 possible second cards, 50 possible third cards, all the way down, right? That's a factorial. Grab your calculators. What's 52 factorial? The factorial button is the exclamation point button. If you have a graphing calculator, you hit the math menu. Math, over here where it says numbers. Probability is on the end, and number 4 is an exclamation point. 52 factorial. Okay, wait a minute. That's an 8 with 67 zeros after it. The lifetime of the universe measured in seconds is a 4 with less than 50 zeros after it. If you shuffle 1 billion times a second since the day the Big Bang happened, you have not gotten 1/100th of 1% of the way through the possible way to shuffle a deck. So if you shuffle a deck, there's a pretty good chance nowhere, anywhere in the universe has that particular arrangement been made before. But there's another side to probability. When you measure height or time, you can measure distances as fine a division as you want, right? And it is actually not discrete because your range of possible outcomes is a continuum, an interval. If I ask you how tall you are, most of you will give me an answer in feet and inches. An interval, even minus infinity to infinity. But you could give me tenths of an inch. If I gave it to you in centimeters or millimeters or micrometers, you could give me your height in angstroms if you really wanted to, right? You could get as many decimal points after the number of inches as you want. So your answer isn't really 5'10", 5'11", there's nothing in between. My sister-in-law is absolutely devastatingly proud of the fact that she is 4'10.5". Because at 4'10", you're required to ride in a booster seat in the state of Florida. She is 4'8". It'd be really embarrassing to be forced to ride in the booster seat, wouldn't it? But I could ask, what is the chance that I walk up to somebody, ask them their height, and they give me an answer between 5'5" and 5'8"? Right? I could ask the probability of an event. And an event is a subset of outcomes that could happen. Now, realistically, I walk up to a person and ask, how tall are you? I'm expecting an answer that's less than, 84 inches. I don't have very many 7-foot people on campus. There are some, maybe. So I'll go up to 90 inches. I don't think there's anybody 7'6". So there's a lot of options here, right? But I could say, what's the chance this person has a height between, 5'5" and 5'8"? 5'5" is 65 inches. 5'8" is 68 inches. What's the chance that my person is taller than 6'6"? You walk up to a person on campus, you can ask, how old are you, right? What is the chance that the person's age is over 20? I don't care how far over 20. You could have been 20 for all of 3 hours, you'd fit in that group. What do you know about those three numbers? These resulting probabilities that come out of me asking these questions. Some people will fall into these categories and some won't, right? Which means no matter what I do, I should expect all of these numbers to be a fraction, to never be bigger than 1, and always be an upper bound, get a fraction. I should never get a negative number. It doesn't make sense for you to tell me the chance of meeting someone older than 20 is -1/10. I don't know how to do that. So I know that no matter what probability I am looking at, this is true. P of E, sorry. Now, this event, age bigger than or equal to 20, has a complementary event. What's the opposite of age bigger than or equal to 20? Say it loud, Maddie. Actually, just strictly less than 20, right? Because anybody who's equal to 20 is already in there. But if I ask you to look at those two probabilities, the probability the age was bigger than or equal to 20 and the probability that the age was less than 20, what do you know about those two together? That's got to be everybody. So that's got to be 100% of the people I asked, that's got to add up to 1. What if I had more options? Like I did with heights, I could break it into ranges, right? And so I could say if I asked all of the possible people, then the total of all of my probabilities should add up to 1. As long as the events I am looking at don't overlap, have nothing in common. Okay. So far, none of this has anything to do with any calculus, so where the hell is calculus coming to the game here? I can think of age or height or whatever as a variable. And I could ask that we write down a function whose output is the chance you are height whatever, or the chance you are age whatever. I want a function that I'm going to call a continuous random variables function. A continuous random variable represents some event we are trying to figure out, some process whose outcome is not deterministic nor discrete. So I want something where the chances are not fixed like that, and I want them to be random in some fashion. So this is a variable. I'm going to look at a function of this variable, and we're going to call it a probability density function. That represents the chance of an event. We'll call it f of x, where x is my random variable, but it could be a or h or any other letter you want. Aha! Here's where calculus comes into play. The chance of x having some set of outcome range is equal to the integral of that function over that same range. So if I want to ask, what's the chance of a person having a height between 65 and 68 inches, I look at the height function and I integrate from 65 to 68. What's the chance somebody's older than 20? I take the age function and I integrate from 20 to infinity. Now there's reasonably an upper limit. No known human being is older than 120 years so far, but I don't know. These two facts. How do those two facts get reflected in my function? If I want to guarantee that the probability of an event is between 0 and 1, what do I know about the function f that I'm using to describe my probabilities? Well, not necessarily A is 0 and B is 1, because we just did 68 and 65 and 68 for heights, right? Those are x values. I'm thinking now about the y values. But I agree with you, that y value should never be negative, because then I might get an area that's negative, and that would screw this part up. And it shouldn't go much bigger than 1. As a matter of fact, it should probably be always pretty small, so that as I add up area, the area never gets bigger than 1. So my function itself can never be negative. And the total area has to add up to 1. Because that's what this right one says up here at the top. It says the total of all non-overlapping events. Well, that's all the different options for x. If I'm adding up all those different options, that's an integral. Now, what's interesting here is that I didn't tell you anything about the shape of this function. I didn't tell you anything about what it represents. And in each situation, there are different probabilistic functions, there are different PDFs that are common. And it depends on what situation we're in as to which one is the most useful. Some of them, we just make crap up. As long as it obeys those two rules, it is a probability density function. An example. Here is a function. It is technically a piecewise defined function. It is equal to this expression for x between 0 and 10, and it's 0 everywhere else. I would like you to graph this for me. I've only defined that function to be non-negative between 0 and 10. And I don't think it's going to be very big because the total area under that curve should only be 1. So that should be a very small, thin, downward opening parabola. I'm a crappy artist, but there we go. And since the function is defined 0 everywhere else, do we satisfy the first condition? Yeah. This function everywhere is either 0 or greater. Do we satisfy the second condition? Is the integral from minus infinity to infinity of this function equal to 1? Do the integral, tell me what you get. Now, your first reaction might be to say some very choice curse words because I'm doing an integral from minus infinity to infinity. And that means I might need to do an improper integral from minus infinity to some number, from some number to infinity. But because of the way this function is defined, I can actually break this integral up into three parts. I can do the integral from minus infinity to 0. Then I can do the integral from 0 to 10. And then I can do the integral from 10 to infinity. Everywhere between minus infinity and 0, what is the value of this integral? Say again? 0. So because the function is 0, this whole part is 0. This whole part, for the same reason, is 0. So it turns out this is actually not a function whose integral involves infinity. It's only a function on a finite part of the axis. Technically, we call such a probability density function a finitely supported density function because it only works from here to here. Okay, I'm going to multiply this out. Actually, I'll take the 0.006 out front. I'll just multiply that through. So I get 10x minus x squared. Do the integral. Evaluate from 0 to 10. When I put in 0, I get 0, so I get 0.006 times 500 minus 1,000 over 3. And that's 1. Yay. So now if I want to ask you a question about this particular probability function, what's the chance that when you do this, your answer is between 3 and 7? What is the chance of that occurring? This no longer is a question about guesses or chance. This is now an integral question. And it's the integral from 3 to 7. Which is something we know how to do. We've just done the integral of this function. And I just have to plug in and evaluate. So the chance of you getting an answer between 3 and 7 when you do this or ask this question is 57%. Every question about probabilities becomes an interval question. This does lead rise to what I think is a slightly strange result. What is the chance that when you do this, you get an answer of exactly 1? What is the probability that x is 1? It should be 0 because that'll be the interval from 1 to 1, right? That's kind of weird though. A continuous random variable makes it very hard to say I'm going to get exactly this. That's an area of 0. But if you ask me, what's the chance you get between 0.99 and 1.01, I could answer that. So there's always some sort of spread, some sort of margin of error required in a continuous random variable. This is always 0. As a matter of fact, the probability for any number is always 0. So you can't predict an exact value with a probability function. You can only predict a range. Questions? There are lots of probability density functions that you've already seen. I asked you to pick a card. What was the chance you got a particular card? There's a chance you get the Queen of Spades when I tell you to pick a card. One in 52, right? And if I ask you what's the chance of any particular card, they'd all be 1 in 52, right? If I gave you a die, a normal standard 6-sided die, and told you to roll the die, the chance of you getting 4 is 1 out of 6. The chance of you getting 2 is 1 out of 6. A function is called a uniform distribution. If it looks like this. The dice were going from 1 to 6. Well, technically, 0 to 6. Right? Chance of 1, chance of 2, chance of 3. And the probability was 1 over 6. The cards were going from 1 to 52, and the probability was 1 over 52. The graph of a uniform distribution is a straight line. But as I start looking at more complicated situations, my graphs start to change. How many of you have had the indignity of having your computer break? Hard drive crash, you had to recover from a backup, your phone bricks out on you, or something like that. You have a light bulb pop. Anybody not had a light bulb pop ever? Okay, come on. Seriously, you've blown a light bulb every now and then. How long does a light bulb last? That's on the package of light bulbs. If you go to Walmart and you pick up an incandescent bulb, it will tell you expected lifetime so many hours. You pick up a CFL, expected lifetime. You pick up an LED, expected lifetime. They're written on the box. How do they know? You go to the bank, to the grocery store, to the registrar's office, to your professor's office for office hours. How long do you have to wait before somebody can see you? How long do you spend in line? You call up the cable company to bitch about your cable and figure out what's going on. How long do you spend on hold? Maybe you're in the chat window. Your next available chat operator will be with you in 73 hours. How long does it take? All of these are probabilistic questions, but they're usually not uniform distributions. Depending on the type of object you have, some of them will have very quick failures. Light bulbs, right? You could buy a light bulb, plug it in, and have it probably means there's something wrong. So there will be a bunch that have short lifetimes, and then the lifetime will get longer and longer and longer and longer for fewer of them. A proportion. Most of these graphs are exponential in nature. So this is a graph that's going down. If it's an exponential, it's e to the something. Let's call this t for time. This is an exponential. It's going down. What do I know about the exponent e to the something? Graph goes like this. It's negative. But wait, there's more. I don't care about negative time, so I'm only going to define this for t bigger than 0. It's going to be 0 elsewhere. I need to make sure that this function has the right integral. So there's got to be some other number in front here. Because if this is like 1, because e to the 0 is 1, then this integral is going to be too big. So there's got to be some scaling in there. Well, there are two numbers here, right? That's annoying. Let's try and figure these out, at least relative to each other. So this is my function f of t. So just like with the previous one, I broke it up into two pieces. Of those two integrals on the right, which one of them can we evaluate directly right away? with no work. Right, because on this entire section, f is 0. So this integral is garden. Poof. So really, I need to do this integral. The integral from 0 to infinity, a e to the minus ct dt. A and c are numbers. I don't know what they are yet. But what do I want the value of this integral to be? I want this value of the integral to be 1. So let's evaluate this integral. This is an integral involving infinity. I need to switch it to a limit. So this becomes the limit. I'm already using t, so let's use x. Integral from 0 to x, a e to the minus ct dt. It's the integral of e to the stuff. Look, it's a u substitution.
I forget they can u maybe. C, there.
Well, let's actually make it the whole thing. So let's use the minus sign as well. Then du is minus c dt. I don't have a minus c, so I'm going to get a 1 over c with a negative du for my dt. The integral of e to the u is e to the u. Switch back. E to the minus ct from 0 to x. So I get minus a over c, limit as x goes to infinity, e to the negative cx minus another a over c with a minus sign, e to the minus c times 0. Wait, what's that? That's 1. E to the 0 is 1. What's this? Leo.
It would be 0. It's like 1 over e infinity. It's like 1 over infinity is 0.
1 over huge, poof, that's 0. So this piece is gone, and I get a over c. Wait a minute, I want a over c to be equal to 1. That means that a and c are the same number. So my probability function looks like this. Every single time. But wait, there's more. I'm going to ask you a geometry question about my probability. I'm putting the picture back up. Picture. Where's the center of mass of that shape? I only want the x value, or t value. Where would I find the balance point? Remember, this goes off to infinity, right? It's really going to be very thin as we go out this way. It's fairly thick at this end. So I would expect the balance to be closer to the left than it is to the right. But somewhere there's a point where the area on the left balances the area on the right. Wait a minute. This is a probability. If I were to think of how much is on the right and how much is on the left, that's taking that X factor and multiplying it back in. If I were to write this, that's X bar. Wait a minute, wasn't there two integrals in X bar? What was the other integral in X bar? Oh, come on, people, I just gave you this homework back. Look at the papers you got. What's X bar? But the integral from a to b, in our case minus infinity to infinity, of f of x is 1. That's the area under our curve, and we just decided that because this is a probability, that area is 1. Technically, it should be divided by this. But I know this is 1. Ladies and gentlemen, the x-coordinate of the center of mass of a probability distribution is the average. So if I want to figure out what the average lifetime of a light bulb is, I need the probability density for our light bulbs. If I want to figure out the average waiting in timeline, I look at what this distribution is, and I find its frickin' center of mass. By the way, for a probability distribution, we usually use the Greek letter mu for a mean. You'll see that in your prob and stats classes if and when you have to take one of those. But we also use X bar for an average for a sample. It's the same symbol because it's the same bloody calculation. By the way, if this is our function, it turns out those two numbers are related. That C in front is the reciprocal for our average, which really means that my exponential distribution looks like this. If I tell you the average time you're going to spend on hold with the cable company is 12 minutes, you now know the chance of being less than 5 minutes, or the chance of being more than 18 minutes, or the chance of being between 7 and 20 minutes. All of those things can be gleaned from just knowing the average time. Who's taken a prob and stats of any type? There's another measure center. There's mean and median. What's the median? What's the word mean? What is the word defined to be? I don't want to use mean because mean is average. What's the median? It's physically the middle. Half of them are down here and half of them are up here. That's not the same as average, because the average takes how far away you are into account, not just where you are order-wise. So the median is the dividing line between the low half and the high half of our data, which means from a calculus perspective, I want the integral from m to infinity to be equal to 1/2. Or I want the integral from negative infinity to m to be equal to 1/2. Which means you could figure out that half of the people will be helped in a certain amount of time in your line by finding m. All you need is the function. Now, it's for this reason that when I like teaching statistics, I teach it from a calculus background. But a lot of people take a stats class that doesn't require any calculus. How do they get away with that? Answer. Somebody else did all the calculus for you and wrote it down in a table. And so instead of you having to look up and do all these integrals one after the other, you can instead go to a table and say, what is the standard version of this formula, and use the integral off of that. But that requires me to standardize my data. Okay. There's a very commonly used curve in stats classes, a commonly used distribution function. What's this one called? A normal distribution, or a bell curve. If I put this at 0, that's the middle. And because of symmetry, that's the mean. That's my average. Then I can actually give the equation for this, depending on how wide or how narrow I make it. Where sigma is the standard deviation, which helps me tell whether I have a wide curve or a narrow curve. The normal distribution has an average of 0 and a standard deviation of 1, which makes doing these functions a lot more easy, and it means I can basically make a table of all the integrals, and you don't have to do the calculus, you can just look it up on a table. For the record, when everybody talks about curving grades, they want me to make my grades fit like this. I hate that idea, because that means there should be as many A's as there are F's. I'd much rather have an exponential looking distribution, where the A's, and then it gets smaller and smaller as we go out here to the B's, C's, D's, and F's. But all of these come back to doing calculus. Now, you could ask lots of questions about where the hell did you get the square root of 2 pi in this damn thing, and why is stuff squared in there? All of that gets answered in the Problem Stats calculus-based course. For now, I promise I will show you where that square root of 2 pi comes from, if you really want to know, but it requires Calc 3. And improper integrals in Calc 3. But it also requires me to do a trick that we have yet to look at, and that's not integrating in X or Y or T, but thinking about other coordinate systems. There's so much more I could do. In probability alone, there's 2 semesters worth of that. I think they're great electives, MA 230 and 235. But if you really don't need statistics, I wouldn't do it. I will see you all on Wednesday. Have a wonderful rest of your day.